So welcome you to this module. So what we have been doing during last couple of lectures is that we were developing criteria to compare one or more estimators asymptotically, in the sense that when the sample size goes to infinity or the sample size is large. We developed two important criteria. One was based on the limiting risk, and that led to the concept of a limiting risk efficiency. The second concept was based on limiting distribution approach, and that led to the concept of a limiting ARE, or asymptotic relative efficiency. Then, if you recall, in your last course, you had studied two popular methods of estimation. One was method of movement estimator, and the second was method of maximum likelihood. So in the last module, we studied the asymptotic properties of method of movement estimators, and we saw that method of movement estimators generally have reasonably nice properties, in the sense that generally they are consistent and they are asymptotically normal. So now what we'll do is we'll study the asymptotic properties of maximum likelihood estimators. So let me write down that as MLE, maximum likelihood estimator. So this MLE, method of likelihood estimation, you've already studied in your last course. Let me just revise whatever you did in the last course. So suppose x1, x2, xn is a random sample. So RS stands for random sample from a population having PDF or PMF f theta, where theta is a vector of k components, let us say theta 1, theta 2, theta k belongs to theta, which is a subset of Rk. What we assume is the functional form of f theta is known. The only unknown quantity is this unknown parameter theta. Then the joint PDF of, let us say, x whole vector as x1, x2, xn is g theta x product, because the random samples were ID, so product I is equal to 1 to n, f theta xi, x belongs to Rmn. So each xi I assume is m-dimensional random vector, and suppose theta belongs to theta. So the first thing which we do is define the likelihood function. Now if we consider for the observed sample value x, so for observed sample value x, or for observed value of the sample, for observed value, let me call this as small x of the sample x, the function which we define as x is fixed. So in this case, this x is the observed value of the sample, and I consider this as a function of a theta. So Lx theta, which is product I is equal to 1 to n f theta xi, as a function of theta, is called likelihood function of observed sample x. Let us try to see what is interpretation of likelihood function. Let us say if everything was discrete, then g theta x is probability that you observe the random sample as x from the population f theta. So this is, in a certain sense, a likelihood or the probability of observing random sample small x from the population f theta. So there are different populations. So what it is giving is, once we have observed the data, it gives me what is the probability of observing this data from different populations. And that is what it says. The likelihood of observing random sample x, which we have observed, which we have at our hand. What is the probability that this observation came from the distribution f theta? Now the true distribution is f theta is unknown to us. I have already observed the data. So what I try to do is, I try to look at for which population this probability is maximum. Or in other words, for which population the probability of obtaining the data which we have already done is maximum. So maximizing, so one should seek population f theta for which this is maximum. And that leads to, so identify population is identified through theta. So I try to look at that theta for which probability of observing the given data x is maximum. So I try to look for a population which has the maximum chance of yielding the given data which we have observed. And that is nothing but maximum likelihood estimator. So I call definition of a maximum likelihood estimator is for observed sample x let theta hat, which is theta hat depends on x, be such that Lx theta hat is maximum. So supremum over theta belonging to theta of Lx theta. Then theta hat is called the MLE of theta. Theta hat x. So of course this theta hat is a function of x. So let me write down theta hat x. Then theta hat x is called maximum likelihood estimate. So I would like to distinguish here between an estimate and an estimator. Estimate is an observed value of an estimator. And estimator is always a random variable. So after you have observed the data, you get an estimate. But before the data has been observed, I have an estimator which is a random variable, and I do not know what its value is. I know that the only thing I know is it is a random quantity, so I can study its properties. So theta hat x, which is a random variable, is called an estimator. So this is the property of a, this is a definition of a maximum likelihood estimator. Now sometimes, as you must have seen in your last course, maximizing log of Lx theta is easier. Note that Lx theta and log of Lx theta are one-to-one function. In fact, log of x is an increasing function. So if theta hat maximizes Lx theta, then theta hat would also maximize log of Lx theta. Why? Because Lx theta and log of Lx theta are increasing functions. So maximizing Lx theta is equivalent to maximizing log of this. So maximizing Lx theta for a given sample is equivalent to maximizing log of Lx theta. Now this function, which we denote by, let us say, small Lx theta, this function is called the log likelihood function. So in many situations, maximizing log likelihood function is much more convenient. So many times we'll work with log likelihood function than the likelihood function. Now one thing you know that when for given x, that means for a given data, if your log likelihood function Lx theta is differentiable, and you know that maximum occurs inside the parameter space theta. So the maximum is the interior point. And maximum occurs at interior of theta. Then by the standard result in calculus, you know that the maximum has to be a critical point. Then MLE, if it exists, is a critical point. That is a solution of the simultaneous equation. So partial derivative with respect to theta I of Lx theta is equal to 0 for I is equal to 1. So maximum likelihood estimator has to be a solution of this under quite general conditions, especially when Lx theta is differentiable for every theta in the parameter space. And you are assured that the maximum always occurs in the interior of the theta, not on the boundaries. In that case, the MLE would satisfy, MLE would be a critical point, or in other words, it would satisfy these simultaneous equations. So now, let us try to see some of the properties of maximum likelihood estimators. So let me write down a few remarks. First remark I say that MLE may not be in the interior, or it may not be a critical point. It may be on the boundary. The MLE, even if Lx theta is differentiable, MLE may not be a critical point. And it may be on boundary of theta. Of course, you can get many examples of this fact. Uniform 0 theta. You have seen in your last result, uniform 0 theta density is 1 upon theta, likelihood function is 1 upon theta to power n. If xn is less than theta, that means theta is greater than or equal to xn. So here, if you look at differentiate the likelihood function, you get as 1 upon theta, you don't get any solution. But what you observe is MLE is xn, which is on the boundary. But here let me give another example, which is non-trivial. So suppose x1, x2, xn are IID normal theta bar. Now normally you assume that theta takes any value in the real line in the normal case. Here let me assume that I know that theta takes only value greater than or equal to 0. So theta is between 0 to t infinity. So I need to find out what is the MLE. So let us try to see what is Lx theta. Lx theta, you must have done it many times in your earlier course. It is 1 by 2 pi to power n by 2, so minus n by 2 log 2 pi minus 1 by 2 summation I is equal to 1 to n xi minus theta whole square. This is what. Now there is only one parameter, so d by d theta of Lx theta is equal to 0 implies that theta is equal to x bar. In fact, let me find out what exactly d by d theta of Lx theta is. This goes away, so minus 2 goes away, so 2 times d by d theta. So 2 times, so this becomes n times x bar minus theta. So critical point is theta is equal to x bar. So critical point is but let's try to see what is the maximum likelihood estimator. To see the maximum likelihood estimator, note that this cannot be a maximum likelihood estimator because x bar can take negative value, where theta is between 0 to infinity. So maximum likelihood estimator always takes values in the closure of a parameter space, which is 0 to infinity. So suddenly if x bar less than 0, this cannot be this thing. But let us try to see what would be the maximum likelihood estimator. So I see the monotonic behavior of this. This will be increasing if this is greater than 0. That means theta is less than x bar. So Lx theta is strictly increasing if theta is less than x bar. Lx theta is strictly decreasing if theta is greater than x bar. Right? So it is this kind of a situation. Increasing and decreasing. So theta is equal to x bar. What I know is my theta is greater than or equal to 0. So now x bar can take any value. It can be less than 0, greater than 0, because in the normal case xi can take negative values also. So I do not know where x bar is. So what would be MLE? Depending on where it is located. Note that if x bar was less than 0. If x bar is less than 0, my parameter space is 0 to infinity, and in 0 to infinity I see my likelihood function is, this is Lx theta. I see my likelihood function is decreasing. So it will be maximum at theta is equal to 0. So this would be if x bar is less than 0, maximum is at theta is equal to 0. Let us consider x bar greater than or equal to 0. That means my 0 is over here. So my parameter space is on right of this. Then I know that my likelihood function increases up to the x bar, and then it decreases. So maximum is attained in this case at x bar. So here you see maximum likelihood estimator does not turn out to be exactly the critical point. It is on the boundary under certain conditions, especially when x bar is less than 0. It is on the boundary of this set 0 to infinity. Another example which you must have already done in your earlier course, that MLE would always be a function of a complete sufficient, minimal sufficient statistic, provided it exists, but it itself may not be a sufficient statistic. MLE is a function of minimal sufficient statistic, provided it exists, but it may not be sufficient. Why? For example, you can look at various examples. Lx theta, so x1, x2, xn. IID, uniform theta minus half to theta plus half. Now, in this case, you know what is your likelihood function? 1 upon b minus a, so that is theta plus half minus theta, so 1, so it is 1. If each xi is between theta minus half to theta plus half. Xi is greater than or equal to theta minus half, that means minimum is greater than or equal to theta minus half. So that means theta is less than or equal to minimum plus half. Each xi is less than or equal to theta plus half, that means maximum of xi is less than or equal to theta plus half. Or in other words, theta is greater than or equal to xn minus half. 0 otherwise. So your likelihood function is this. So your likelihood function is constant. So if I take any value between xn minus half to x1 plus half is the MLE. So any value between xn minus half in xn minus half to x1 plus half is the MLE. In particular, x1 plus xn by 2 is MLE, because x1 plus xn by 2 lies in this interval, b plus a by 2. b plus a by 2 lies is MLE. It is clearly a function of a complete minimal sufficient statistic x1 and xn, but x1 plus xn by 2 itself is not sufficient. And why it would always be a function of a minimal sufficient statistic? Because you are trying to maximize the likelihood function. And you know that likelihood function can always, by factorization theorem, can always be written as a function of a minimal sufficient statistic if it exists. So your likelihood function is always a function of a minimal sufficient statistic. So that means you're maximizing something which is a function of minimal sufficient statistic. So the solution which you get as a maximizer has to be a function of minimal sufficient statistic. Now this example also suggests that MLE may not be unique. Now even if Lx theta is differentiable and the maximum is in the interior of the parameter space, the likelihood equations might have a multiple roots, and you do not know which route to take. So even when log likelihood function Lx theta is this smooth, and MLE is in the interior of theta, the simultaneous equations del by del theta I Lx theta is equal to 0 for I is equal to 1 to k may have multiple roots. Once they have multiple roots, what you know is they are either points of local maxima or local minima. So they are points of local maxima. So in that case, what you have to do is you have to verify each and every root to see whether it is a global maxima or not. And various roots have to be checked for global maxima. So usual thing which you do in calculus when you deal with a function, you try to look at the function and see where the maximum exists. So the only possibilities are, if your function is differentiable, maximum would be either in the boundary or in the critical point. So you try to see whether I can rule out maximum being in the boundary. If that is the case, then you look at only the points where critical point is there, but critical point also correspond to the minima. So you examine each and every critical point and then try to narrow down on the global maxima. Now let me write down the check which you use in your standard calculus course for maxima or minima. So this would be fifth. So let us look at theta x is collection of all those theta belonging to theta such that Lx theta is positive. Because I'm talking about log likelihood. So I need likelihood to be greater than 0. So I try to look at the Hessian matrix Hx theta as, in fact, I can talk about Lth Hessian matrix, or first let me define Hx theta as the Hessian matrix del Lx theta, del theta I, del theta j. So its ijth element is this. So of course, this would be k cross k matrix. And let us look at Hxl theta. This is a matrix obtained from Hx theta by deleting last k rows and last k minus l rows and last k minus l columns. Matrix obtained by deleting last l minus k rows, k minus l rows and k minus l columns of H. And this for L is equal to 1 to k. So this is Hxl. Let me write down very clearly. So for example, Hx1 theta is what? The matrix obtained from here by deleting last one row and last one column. So it would be k minus 1 by k minus 1 matrix. What would be Hx k minus 1? I delete last k minus 1 rows and last k minus 1 column. So it would be a 1 by 1 matrix, which would be del Lx theta by del square theta 1. And then L is equal to k, matrix obtained from this by deleting 0 rows and 0 columns. So Hk theta would be Hx theta itself. Now you know, depending on the eigenvalues of this, you can determine whether a point is, critical point is a local maxima or local minimum. So what I assume is let theta hat x, which is theta 1 hat x, theta k hat x, be a critical point. Then what do you know? I can determine whether it is a local maxima or local minima. Then theta hat x is a local minimum if Hx theta hat x is positive definite, which is equivalent to saying that determinant of each of those matrices Hxl theta is positive. Or, in other words, all eigenvalues of Hx theta hat are positive. positive. Or determinant of each of those matrices is greater than 0. Is positive for L is equal to 1 to. Now B, you can say that this is a local maximum, which should be the thing you would be looking for because you have to find the global maximum. If hx theta is negative definite, that is, if eigenvalues of hx theta hat are negative, or each of those determinants or the determinant of each of those matrices is less than 0. Now, there is a concept of a saddle point. That means this from one direction, if you look at it in 3 dimensions, it may look like a maximum. From the other direction, it may look like a maximum. So that means, although it is a critical point, but it is neither a maximum nor a minimum. So theta hat x is a saddle point if S theta hat x has both positive and negative eigenvalues, but determinant is non-zero, and certainly this test is inconclusive if determinant is 0. Test is inconclusive. So these were some of the properties of maximum likelihood estimators, which you must have done in your last course. The purpose here was just to refresh them so that you are on top of these properties. Next module, I'll again study some more properties of maximum likelihood estimators, and then I'll go to the asymptotic properties of maximum likelihood estimator. So that's all for this module. See you in the next module. Thank you.